Hi everyone, this is MickMake Mail number 42.
Yes, but you're not going to like it.
And I've got a couple of packages to unbox. Let's get into it. This video is being sponsored by JLC PCB. JLC PCB can manufacture prototype PCBs from 1 to 6 layers with track widths down to 3.5mm. They also support pretty much everything you can throw at them, so check the description below for a list of all their capabilities. For only $2 you can get 10 PCBs manufactured within 24 hours. And if you are a first time customer, you can get $20 off shipping off your first order. So I picked up a mini toaster oven from Aldi, so let's open that up first and see how that goes. So this is the toaster oven, and I originally thought it was going to be a little bit too big, but I think it's actually probably going to be fairly good to toast PCBs. Got a fair amount of space in there. So first of all, I need to see how fast the oven gets up to temperature. That's the most important thing. If it can get up to temperature within a reasonable amount of time, then I can possibly convert this over to a reflow oven. So I don't think I'll be using this sort of rack, but I might definitely be using this aluminium tray. I reckon if the PCBs are laid flat on this tray, it'll be quite good. So I'm going to use Dave Jones's meter just to keep track of what temperature this oven gets to in a certain amount of time. So I've hitched up the meter, and as you can see I'm tracking the temperature. It's sitting about 25.6 degrees Celsius, which is about right. It's not summer, so the temperature down here is a little bit cooler. Okay, I'm going to whack it on the maximum and I'll give it 40 minutes, but it shouldn't need that much time. Great sound. These are very cheap things, so it's perfect for being able to control using a PID. So the temperature's not rising, which is a bit strange. Maybe I haven't turned it on. I've got to turn it on. Okay, so there's a setting which turns on either the top element, the bottom element, or both. So the sensor's sort of sitting on the left side, it's not actually sitting in the middle. So let's see how quickly it can get up to temperature. You've got to love those mechanical timers. Okay, so it's been a while. It's just getting up to about 50 degrees, 51 degrees. I think it's pretty slow. But we'll find out after I actually collect the data and see what it looks like. Okay, so things are starting to heat up pretty quickly now. It's up to 110 degrees, which is good. So I can hear the thermostat clicking on and off, which is a bit odd because it hasn't even reached the 240 degrees Celsius yet. So it's up to, 167 degrees Celsius. It's almost at 230 degrees, the maximum temperature can go to. So I think that's looking pretty good. I think the ramp up temperature is pretty good, and because it's a small unit with not, oh man, that's hot. So it's because it's a small unit, not much insulation there, the ramp down actually might be pretty good as well. So the oven's trying to turn the elements on and off, and you can see that sort of hysteresis effect, as I explained in one of my other videos. So you'll see that sort of sinusoidal wave that's appearing. So I reckon this is a goer. This could actually be quite good as a reflow oven. Nice compact size. So when you're actually cooking PCBs in a reflow oven, the ramp down is just as important as the ramp up. So I'm hoping that the ramp down will be able to fit within a nice temperature profile for reflow ovens. So the unit's taken a while to come down in temperature. It's sitting around about 90 degrees Celsius, so that's not really too much of an issue. because I can always add a fan to the side or the back and control the ramp down from that perspective. So I reckon this is still pretty much a goer. So looking at the data I gathered, the ramp up rate is a max of 2 degrees every second, which is good. This puts it in the mid-range for ramp to soak and also ramp to peak on a standard reflow profile. So I may be able to fiddle with this and get it to ramp up quicker. I'm guessing that there's probably some sort of thermal ramp up protection in the oven, but I won't find out until I do actually crack it open. However, I'm not going to do that now. I'll wait for one of Xeon's Reflow Oven controllers to arrive. So, on to the next thing. Okay, so the next thing, this was an order I placed with Mouser. So these are most of the components that I'll be using for the wyrks-UPS board. They're all pretty much standard components, 8 picofarad caps, micro USB, 32 kilohertz crystal, 10 picofarad cap. So I bought a couple of picofarad caps because I wanted just to make sure that my calculations were correct, and if they were slightly off, then I could just drop down to another value of capacitor. So these capacitors are for the crystal. So what else we got? This one is the microchip 7940 RTC. It's a fairly sort of stock standard RTC, but it has a fairly low quiescent current, which is nice. That's something I need for this particular project because I wanted to be able to get the quiescent current as low as possible. Very important. So this is the ATtiny416, which I'm basing the wyrks-UPS on. So I got these boards so I could confirm my design before I started to populate the PCBs. So hopefully I'll be able to do a couple of quick tests on these boards just to confirm my design assumptions. And I did actually request these to be delivered in a reel, but they didn't do it, which is a real bugger. The reason for a reel is because I've got 200 of these components and I didn't really want to have to do this by hand. So this is the IC that I mentioned in the WS2812 video I published a while ago, and it's quite suitable to be used to drive WS2812 RGB LED strips. So it's just another way instead of using the 8-channel logic level converter. And it actually ends up being slightly cheaper. So, and all I needed was 3 channels for that particular board. So I bought a whole stack of them. And yes, this will be something that I'll be using in the Wyrks Pi IO, along with a whole bunch of BSS 138s. And lastly, this is a Kickstarter I backed some time ago, and when I was looking through a bunch of my Kickstarters, I noticed there was one that wasn't actually delivered. So I don't know why it didn't end up being delivered, but I contacted the campaign creator and he was very understanding, and it seems that my package was actually returned for some reason. I don't know why. But anyway, he was very understanding and he had this package listed as one of the items that wasn't delivered. So he just sent it again, which is nice. Very professional. So this is a DACBerryOne. This was something that was on Kickstarter 2 years ago, I think. It was in my undelivered list for that long, and I just didn't chase it up. So it's no fault on the campaign creator. So I know it's a fairly old board by now, being 2 years later, but I think I need to give it a bash and see how it goes. So I think I'll check it with some headphones, which isn't really going to be doing it justice. Yeah, so once again, headphones really aren't the best way to be checking the sound, but you can hear a very subtle difference between the two samples. Yeah, I don't know, it's going through headphones I think would be not so good, but being able to push the sound out through digital out into a proper amplifier will certainly make things a whole lot better. But yeah, this is a really nice board made by OSA Electronics. It's a fairly old board, but yeah, it works really well. Anyway, let's get on to the next thing. So one thing I started to do is buy these extra long headers. So it means when I solder them onto a board, there's actually a little bit of extra header space at the top. So it gives me essentially another connection. So I can either use it in a breadboard or without. You can get them from Element 14 and a whole of other places. There's just enough sort of play to be able to chuck one on top, as long as you don't solder too much up the end. So yeah, that's quite good. So you can see after soldering it still has a bit more space at the top to be able to add a jumper, and it just fits. So it just gives you some more expansion options if you want to be able to connect on the top or through the breadboard or whatever. So let's fire this up and see how it goes. So I've just added a little LED so I can just do a simple blinky program. The interesting thing to note with these boards is that the AtTiny isn't actually this. This is just an ATmega, which is something that's used to be able to program the AtTiny. So this is actually the AtTiny. So it's a pretty tiny little thing. These boards come with no crystal on board, I believe. So they're driven by internal clock. So let's see how that goes. So currently the ATtiny416 isn't supported under the Arduino IDE. There's going to be a board that Arduino will produce which contains this AtTiny. So until they've actually come up with the Arduino core for that particular MCU, we won't be able to use the Arduino IDE. So I have to use Atmel Studio. Of course it forces me to use Windows as well. So there's a couple of things I need to actually test out. So since I'm going to be using this as part of my wyrks-UPS and also the micro-UPS, there's a couple of things I need to actually check out and test. One of the things that I'll test first is the ability for the AtTiny to be able to measure the input voltage, or the VCC, without any external logic. So that's important because I want to be able to keep the cost of this whole micro-UPS down as much as possible. Okay, so there's an application note that Microchip has written which covers the ability to be able to measure the VCC or battery voltage without using any I/O or any other external components. So it essentially uses the internal reference voltage, which is VBG, which acts as the ADC input, and then uses the target VCC as the ADC reference. So you can actually get a fairly decent voltage sort of reference, but I actually do need to test it out to make sure it is actually as accurate as possible. So what I'll do is I'll chuck it into the existing USB, and there's actually a 0 ohm resistor down here which I can remove, and also provide a separate voltage and vary the voltage so I can see how accurate it actually is. So let's try that method out. So what I've done is I've put in a fairly simple C program using the Atmel Studio, and all it does is print out VCC. So I haven't done any debugging prints or anything like that. All I'm doing is every 500 milliseconds I'll set the value of VCC, and I've set a debug point, so when I loop through you'll be able to see the VCC value change. Defaults to 0 volts, and then the next invocation it flips around to 5.06. Now theoretically this value here, according to the application note, this should actually be 1.1 volts, but I've done a bit of playing around and I've discovered that it's actually 1.5. To show you an example, the reading that I get from the current VCC, so I'm getting 5.06 volts, and the VCC value from the AtTiny is coming up as 5.06 volts, so it's about accurate. So I found out I had to actually apply a 1.504 multiplier. But to confirm that, what I need to do is actually then to remove the 0 ohm resistor from here, which provides 5 volts to the AtTiny. So what I'll do is I'll lower the voltage, maybe set it to 3 volts, even 2 volts, and see how it actually responds and see if it is actually accurate across a full sort of voltage range. So what I've got here is my trusty benchtop power supply connected up to the 2 rails on the breadboard, and I've disconnected the 0 ohm resistor, so this side is separate from this side. I can power the 5 volts and the ATmega 32U4 from this side, and this side is completely floating. So first of all, I'll start off with a 5 volt, 5 volt power supply. I've limited the current to 100 milliamps, and let's see if we can actually get some sort of response. When I drop down to certain voltages, of course, I'll lose connectivity from the AtMega32U4 because of logic levels. I should be able to get down to 3.3 volts, maybe even 3 volts, but let's see. If it gets too low, I might have to chuck in a voltage level translator in there, but let's see. Okay, so now we're registering 5 volts, which is about right because I've set it to 5.00 volts. That's as accurate as I can get this particular benchtop power supply. So it's looking pretty good. Now I'm going to do a fairly risky move and adjust the voltage. Let's see if I can drop it down to 4.9 volts. Okay, still registering 5 volts. Maybe it's just the tolerances. Let's drop down to 4.7. Still registering 5 volts. That's really weird. I don't know why I'm still registering 5 volts. Let's drop it down to 4 volts. So that's now down to 4 volts. Still 5 volts. What's going on? So one thing I discovered is that there's a register for the analog to digital converter, which starts the whole process of doing an ADC conversion. So all I did was move this statement down into the while loop. Setting the command bit within the ADC register will start the whole conversion process off. So of course, yeah, that was one of the things I was missing. I wasn't actually seeing the ADC update in value. So currently I'm seeing 4.5 volts. If I drop it down to 4 volts, you can actually see the value update. So let's try dropping it down to maybe 3.5 volts, see how that goes. So 3.5 volts. So my bench power supply can only go to 2 significant digits, so all I'm seeing is 0.50. It's looking pretty good, so let's drop down to maybe 3 volts, see how that goes. Okay, 2.9, so it's looking pretty accurate. The internal ADC, being able to measure that, let's go to 2.5. Oh, look at that. It's actually picked it up. So the AtMega32U4 has actually managed to talk to the AtTiny, and the AtTiny is running on 2.5 volts. It's picked up a fairly accurate voltage level. That sort of level is good enough for me. And see, it's managed to pick up 2 volts. So yeah, it's working really well. Let's drop it down to 1.8 volts, which is right on the edge of the AtTiny minimum VCC it can handle. Yeah, okay, so it looks like the AtMega has finally given up the ghost. It won't be able to see the AtTiny. Let's bump that back up to maybe 1.9 volts. Yeah, it's looking like 2 volts is pretty much on the edge, which I expect. So, but that doesn't really matter, because what I'm doing is using the LiPo battery to power the AtTiny. If a LiPo battery ever gets down to 2 volts, then we're in serious trouble anyway. Okay, so there's several other things I need to be able to test for. So I've tested the voltage measurement, which is adequate for my needs. The other thing I need to actually test for is the real-time clock. I actually designed in an RTC, which is an ITC-based RTC on the board. The reason for that is I can always remove that component. It's always harder to add another component, but it's very easy to actually remove a component. So if it turns out that the RTC is not good enough in terms of timekeeping, then I'll have to be forced to use an external RTC. So this is very important because there's been a lot of drift with these AVR microcontrollers, and you can get a drift of maybe 10 seconds over a week, or a couple of seconds over a week. I'd planned for these boards to be able to be used in offline mode as well as online mode, so they need to be able to keep pretty accurate time. So anyway, I need to test RTC. The other thing I need to look at is also power requirements. I need to make sure that I can get this AtTiny down to a very, very low sleep current. I need to check out all these sleep modes to make sure that they actually function properly. Brownout detection, all this sort of stuff. So they're very important, and because it's a fairly new AtTiny, it'll take a bit of time to actually go through. So I won't be able to do it in this mailbag. I think that's all for now in terms of testing this board.